Well, guys, today I have brought you a beautiful video for you. In this video, you are going to learn the complete chapter of NCERT Class 12th Physics book. That is, I am speaking about the first chapter of Physics NCERT Class 12. This chapter is for electric charge and electric field. In this video, I have covered everything, theoretical part as well as the all the questions of NCERT book. The complete exercise is there, and in this video you can see their solutions also, which I have done. If you see this video completely, I don't think that you will require any other reading of this chapter. So, since I am covering the complete chapter, apart from the chapter theoretical portion, I have given you the notes also in this video, which wherever you like, you can pause and take down those notes. So that way, this video is very long. But if you see from inception to the last this video, then I don't think that you require any other reading or any other revision. Everything is I have covered in this video. So let us go to the video. Before going to the video, I would like to say, if you like this video, please subscribe my channel. Also in the comment box, please tell me how do you like this video. Another most important thing, if you want a PDF copy of this complete video, complete handwritten, typed PDF copy of this lecture, then you can send me the request in the comment box with your WhatsApp number or email ID. I will share the PDF copy also with you. So this is very important for the people, for the students who are going to class 12th, and their first most important chapter is that is electrostatics, and among electrostatics, this is the first chapter, that is electric charge and the electric field. So let us go to the video without wasting your time. So before your screen, we are talking about the electrostatics chapter, NCERT's first chapter for the class 12th. In this chapter, we are going to speak about electric charge and electric field. First of all, let us see what is electrostatics. I have given you the definition here. Electrostatic is a branch of physics that deals with the electric charge at rest and the forces, fields, and the potentials associated with them. So what it means, electrostatics basically, it is a branch where we will basically study about the electric charges, and the two electric charges which are at rest, means they are at stationary charges, correct? And when they are stationary, then on each other they will have forces. Due to the stationary charges, there will be electric field, and due to that there will be potential also. All these things we are going to deal with in this electrostatics chapter. Now, if you talk about a simple definition is electrostatics is the study of forces and interactions between stationary. So our main thing is we are talking about stationary non-moving electric charges, correct? So charges are not moving, yes, because we are talking about stationary charges and interaction between the charges. Suppose one charge is there, plus charge is there, and minus charge is there. There will be interaction between two charges. This we will see through the Coulomb's law. The examples you must have seen, like these type of things you have seen in your earlier classes. Whenever your comb, if you rub your comb with your hairs, what will happen? It will attract the bits of papers. How this is happening? Because of transfer of charges that we will see. You must have seen if you rub a balloon from your hair, you can stick it to the wall. So this is due to the interaction of basically charges only. This happens. Next, electrostatics. Let us see what are the main features of this branch, electrostatics. So electrostatics basically we deal with where the charges are stationary. We know charges are two types, positive and negative. Like charges repel, unlike charges attract. This we have already studied. Then since they are repelling or attracting, that means there is some kind of force between them. Correct? So that we will also see. All these forces, how it is happening, it is explained by the Coulomb's law. Then, since there is a force, the charges have their own influence of field. Because of that we define electric field, the region around a charge where force is experienced. Correct? Then what is electric potential? Basically, work done in bringing a charge from away. All these things we will study in detail in the subsequent chapters. Then you are going to study superposition principle also. That when there are number of charges, how you are going to find out the forces on a single charge. Then what is the conservative nature of charges? Correct? You must have studied there are some forces which are conservative in nature. Likewise, this Coulomb force, this force is also, it is a type of central force. So that is also basically conservative force. Inverse square law, this force varies, or you can say this force, Coulomb's force, varies inversely as a square of the distance. So all these things we are going to study. This force is medium dependent also, correct? And there are lot many applications like printers, photocopiers, or pollution control, or all these things. It is basically the charges play a very important role in all these fields basically. Correct? Now let us see, before going to the detail of the charges, how they are behaving, what is the force and all, let us see the historical overview of the how the charge was discovered basically. That is most important. So it is not today basically. In 600 BC, your Greeks, some Greek philosophers they were there, they noticed that when there is a amber is a substance, when you rub this amber with a stone, then it starts attracting small objects. As we have seen today, your comb starts attracting bits of papers. So this was the first observation known regarding the static electricity. Means they found there is something more is there. Why this is able to attract the small objects, this amber, after rubbing. So this was the first development, yeah, or it was just developed miraculously. Now, birth of electricity, you can date back to 1600. William Gimbert studied the electric effects systematically and coined the term electricus. Basically, there is a Greek word, electro, come. Maybe because of that, this they coined this word as electricus. He was also able to distinguish electricity from magnetism. Means that time certain stones, means the naturally occurring magnets, they were also found, and they also the magnets start attracting the iron pieces. That was also a very miraculous discovery. So William Gilbert, he distinguished electricity. It means electricity is something else. This type of charges or this type of attraction is something else, and other type magnetism, that is other type of attraction, is something else. In 18th century, basically, Charles Dufour, he proposed that there are two type of charges, positive and negative, and established that like charges repel and unlike charges attract. Then Benjamin Franklin, because basically he was the American president and he was a great experimenter also. He has contributed a lot of in the field of electricity. So Benjamin Franklin introduced the concept of positive and negative charges and demonstrated that lightning is electrical in nature through his kite experiment. Actually, this kite experiment is very important. If you want, you can Google it. You can study about this. It's a beautiful experiment. Rather, बेंजामिन फ्रैंकलिन की जान जाते जाते बची थी इस एक्सपेरिमेंट में. But he used to see whenever there is a thunderstorm, then there was lightning, and he demonstrated this lightning is nothing but it is in electrical in nature. Then in 1785, the most important formula, that is Coulomb's law. Coulomb's law was basically given by Charles Augustin de Coulomb. He quantified the electric force. Charges, there were two charges. It was established like charges, they repel each other. Unlike charges, they attract each other. Means repulsion and attraction, there are two kind of forces. And he quantified the, these electrical forces using a torsion balance and established the inverse square law of force between the means. He found that this force is basically inversely proportional to the square of the distance between the charges. Correct? Charge quantization. Yes, we always study charge is quantized. Means charge is not a continuous, basically it is the integral multiple of the fundamental charge, that is your electron. Now, in this charge quantization, Robert Millikan measured the charge of an electron using the oil drop experiment and proved that charge is quantized. Means there cannot be fraction of charge. It has to be integral multiple of the fundamental charge, that is electron. Modern development, if you see, electric charge is now understood as a fundamental property of the matter associated with particles like electrons, protons, and explained by electromagnetic theory. This is all we are going to see. So this was the basically overview of historical development of charges to give the more clear examples of static electricity. You must have seen your comps attracting the bits of papers, balloon sticking to walls, spark when touching the metal. Suppose if your door metal, so metallic door knob is there, it is already having a charge, and you just happen to touch that, you will feel a little shock. So the sudden, it is basically due to the sudden discharge of accumulated charge. Correct? This happens. This is basically electrostatic discharge. Correct? Now, hair is standing at the end means if you rub your hair with the balloon, or you rub your hair with the charged comb, sorry, if you rub your balloon with the hair, what will happen? Hair will acquire some kind of charge, that will be one type of charge only. Now, since it is a one type of charge, either positive or negative, since the charges repel each other, that's why your hair is stand up. Correct? Bending of water streams. Correct? Bring a charge comb near the water stream, water bends because the water molecules, they basically, water molecules are polar molecules. They are aligned with the electric field basically. Correct? This is due to the dipole interaction. That we will see what is dipole. In photocopiers, printers also, basically we have seen the this was the because what is this working? Charged drum attracts toner. Controlled electrostatic forces create image, and this is how your type is your printer is able to print basically. Correct? So these are the applications. If you, I have given you all sorts of this thing. Now we will talk about what is basically electric charge. Right? Definition of electric charge I have given ready-made. Electric charge is a fundamental property of the matter due to which it experiences electric force when placed in an so the definition of electric charge you can write in many words. Electric charge is basically it is a fundamental property of the matter due to which it experiences electric force when placed in an electric field. Or in simple words, charge is the property that causes attraction or repulsion between the objects. Correct? You must have seen in your gravitational chapter in class 11 that two masses, they attract each other. Here, in case of charges, like charges, they repel, and unlike charges, they attract. So, though both the things are there, repulsion is also there, attraction is also there. In gravitational chapter, you have seen only attractive force is there between the masses. Types of charges we have seen: positive charge, that is proton. Every matter contains every matter contains atoms, and in the atoms there are protons, and negative charge is there, electrons. So there are two type of charges, and like charges repel and unlike. All these things we have. Now properties of electric charge. Properties of electric charge is basically additivity. Additivity means, suppose you have +2 Coulomb charge, then -3 Coulomb charge, or and +4 Coulomb charge on this body. Then what is the net charge? Net charge is basically total charge, that is the net charge, that is algebraic sum. Means +4 Coulomb +2 Coulomb -3 Coulomb. That means 3 Coulomb plus. So additive means charges are basically plus and minus. Algebraically, you have to make a sum. So this is the called additivity of the charges. Conservation. What do we mean by conservation of charges? Charges cannot be created or destroyed. Means you have to read this line carefully. Basically, suppose you have one body charge is there +2 Coulomb, another body 5 Coulomb. Correct. Now, if you happen to join them, then what is the total charge? That is 7 Coulomb plus 7 Coulomb. Total charge, or you can say the net charge, is always conserved. Correct. So the net charge is always conserved. Correct. Charges, if they are there on somebody, they cannot go anywhere. Or even if you rub two substances, one become positive, another become negative. How this happens? It is because of the transfer of electrons. Correct. No new electron is created or proton is created. Correct. From one body, there will be transfer of electron to other body. Correct. One will become positive, another will become negative because of the excess or deficiency of the electrons. Correct. Then quantization as, see, this is the fundamental. The charge of electron, that is 1.6 into 10 raised to -19 Coulomb. This is the elementary fundamental charge. Correct. Any charge will be there, it will be in the multiple of this only. Correct. Like Q is equal to NE. N is what? This is the integer. Correct. So it has to be in the multiple of this. Then another important thing, charge is basically it's not a vector quantity, it is a scalar quantity. It has got magnitude only, and charge is also invariant. Means whenever, suppose if you give a speed, give a velocity to the charge, the the quantity of the charge does not change, it remains the same. Or even if you change the frame, suppose you cannot say कि value of the charge in one frame is something else and value of the charge in other frame, if you measure, it is something else. No, it does not change, it is invariant, basically. Correct? Now SI unit, basically unit of charge is basically coulomb, and coulomb is basically one atom. Like basically, what is your I is your current, and this is charge passing through some wire in a unit time is called current, basically. Correct? So fundamental physical unit is basically this ampere into time. That is the basically meaning of this. 1 coulomb is nothing but equal to 1 ampere into 1 second. Correct? So dimensional formula also of charge is basically A into T. Correct? Then I have given you this value of fundamental charge, electron and proton both have the same magnitude, but electron is minus 1.6 into 10 raised to minus 19, and proton is plus 1.6 into 10 raised to minus 19. Correct? Nature of charge you have seen, positive, negative, scalar, coulomb. The smallest value of the charge is this. And quantization means, now this is the Coulomb's law that we are going to study in detail in the coming chapter. Coulomb's law is basically this: 4 pi epsilon 0 q1 q2 upon r. We will study in detail, so don't worry. This is the basically force between the two charges. Suppose both the charges are positive, then q1 will exert a repulsive force on q2, and q2 will exert a repulsive force on. So this F, basically this F is given by this, and R is the distance between them. What is this? This is the constant. It is called K also, and it is a constant. Basically, we will see in the coming slides. Correct? Now we will go again a theoretical part of this, which is given in our chapter. I am not going to take much time on this. Charging by, this is a method of charging. How you can charge a body. Charging by friction. You have seen COM and here. So two neutral objects rub together like this, glass plus silk or plastic plus wood. When you rub them, you give them energy, and the electrons, when having the energy, they are transferred from one body to another body. And due to that, one becomes negative and other becomes positive. Correct? So like comb rubbed with hair, balloon with wool. ठीक है, correct. Charging by conduction means you have to touch. Suppose you have a body, positive charge is there. If you another body is there uncharged, now if you bring this body and touch this charged body, then what will happen? You touch them and then just move it apart. Then what will happen? Both will have now charge will be transferred. Of course, if they are identical body, then equal amount of charge. If they are identical bodies, so suppose you have Q charge here, plus Q is there. It is Q is 0 here, but if both the bodies are identical, you touch them and move it apart, then what will happen? It will have Q by 2 and Q by 2. Okay? Correct. Then charging by induction. You can charge the body by induction also. That can be done like this. Suppose you have a uncharged body, then you bring a charged rod. Rod is having suppose negative, glass rod is there, negative charge is there. What will happen in this sphere A, body A, there will be redistribution of charges. Means due to the negative charge, positive charge will be polarized here and negative charge will be polarized here. Correct. Now what you can do, you just earth this face. Once you earth this face, what will happen? These excess electrons which are on this side, they will move to the earth. Ultimately, what will happen? There will be deficiency of electrons in this body. And once you remove the rod, then this, due to the deficiency of the electron, because electron have been transferred to the earth, due to the deficiency of this positive charge will be all over the body, and this is how you can obtain a body with positive charge. Correct? So this is basically due to the induction. You have not touched your glass rod to the body. So uncharged body has been charged. Correct? So whenever due to friction, both the bodies which are you are rubbing each other, they will have opposite charges. In conduction, basically since you are touching, so both the bodies will have same charges. Due to the induction, you will have opposite charges without power. Like glass rod is your negative, and here in this, it is now become positive. So this is how you can charge the bodies, and these are the methods of charging. I have given you one by one all the three methods with detailed notes. Correct? Now let us go further. Now here comes the basically fourth part, Coulomb's law. Coulomb, what it says basically, The electrostatic force between 2 point charges is directly proportional to the product and inversely proportional to the means. Suppose you have one charge here, one charge here. This is Q1, this is Q2, and the distance between them is R. We assume that these are positive charges, though they will repel each other. Like that means they will have forces. Of course, F12 will be equal to minus F21 because forces will be up. These forces will be equal to each other in magnitude. Of course, they have different direction. One is in the positive x direction, another one is in the negative x direction. Correct. So whatever this F12 you can say or F21 and what this F, this is the this is so this F is basically is proportional to Q1, Q2 and inversely proportional to. So if we remove the proportionality sign, then it is basically K Q1 Q2 upon R square, where K is nothing but 1 by 4 pi epsilon 0. Correct? Value of this K is basically 9 into 10 raised to 9 Newton meter square upon Coulomb square. Correct? What is this? This is the permittive permittivity of free space. So medium is also very important. Correct? So this is called inverse square law. Means the force basically depends on the distance. As the distance increases, the magnitude of the force decreases very rapidly. Correct? So here we have seen mathematical expressions I have given you. Value of the constant is also I have given. Nature of forces is same charges repel, opposite charges attract. Of course, suppose you have negative, one is positive, another one is negative, and they are r distance apart, then of course now the direction of the force, because they will attract each other. So direction of the force will basically F. Again, these two forces will be equal and their value is nothing but, or you can say Q K Q1 Q2 upon R square. Correct? Coulomb's law has some limitation. This is valid for point charges at rest and basically size of the charge should be very small in comparison to the separation between the charges. Correct? So a little bit of notes I have given and let us see what is the vector form of this Coulomb's law. So suppose this is your x-axis and this is your y-axis. you have a Q1 charge here and another Q2 charge here. The position vector of Q1 charge is R1. Position vector of Q2 charge is R2. Correct. Now, since these two charges, they are basically, suppose if we assume they are positive, this is positive, this is also positive, then what will happen? They will repel each other, and this will be the force. Of course, this is your F21 and this is your F12, like we have seen earlier. Correct. What is this? This is your basically when we take F12, this is your R12. When we take R21, this is your R21. Of course, and vector form of basically this, you can write it as, suppose you are writing F12 in vectorial form, then it is K Q1 Q2 upon R1 minus R2 whole square. And then, of course, since left side is vectorial form, so right side also you have to write the unit vector of this R12. What is this? R12 is nothing but R1 minus R2. I hope vectorially, if you see, this is, you can understand, you have seen the vector, you have studied vector in your class 11th. So this is the vectorial form of the, if you want to write F21, then K Q1 Q2 upon R R2 minus R1, then of course magnitude of this, and then unit vector. So this is the vectorial representation of basically Coulomb's force. Correct? Here, one more thing, actually, here we have given, what is this? This is epsilon naught, and its value is also basically, if you can find out, its value is basically 8.85 into 10 raised to minus 12 Coulomb square n minus 1 m minus 2. This is the basically permittivity of free space, basically, or you can say vacuum. For air also, it is taken as the same value. Correct? Now, let us go further. Here, basically, a few questions are also given in your NCERT book as a example. So since I am making the complete NCERT book for chapter 1, this video, so I am covering these also. So let us see these questions. If 10 raised to 9 electrons move out of a body to another body every second, then how much time is required to get a total charge of 1 coulomb on the other body? Means from one body, charge is transferring at the rate of 10 raised to 9 electrons per second. So in 1 second, What is the total transfer of charge? That is basically 10 raised to 9 electrons are there into the charge on the one electron is 1.6 into 10 raised to minus 19 coulomb. That means it is 1.6 into 10 raised to minus 10 coulomb. In 1 second, this much total charge is transferring from one body to another body. Correct? So, how much time is required to get total charge of 1 coulomb? So, total charge, the time required will be what? Total charge is your 1 coulomb which we have to transfer, and in 1 second is this much amount of charge is transferring. Correct? So, if you divide this, it will come out as 6.25 into 10 raised to 9 second. Correct? If we convert this charge into years, means 6.25 into 10 raised to 9 divided by how many days are there? 365. Then every day is 24 hours, and in every hour, this much seconds are there. That means if you calculate it, means 198 years will require with this rate of transfer for getting a total charge of 1 coulomb on the other body. So that means what it shows means this 1 coulomb is a very large unit for practical purposes. Correct? So that's why generally we deal micro coulomb or nano coulomb in the units of micro coulomb or nano coulomb charges. Let us go to the another question. How much positive and negative charge is there in a cup of water? Water, water we have 1 mole of H2O. How much it weighs? 18 gram. Suppose cup of water, actually they have not given the amount of the water. We can assume that. Suppose in the cup there is 250 gram of water is there. Correct? So, so how many number of molecules? How many number of molecules will be there in a cup of water? That will be basically 250 divided by 18 into, we have to multiply by this with Avogadro's number, because in 1 mole there are this much number of molecules are there. Correct? So this is basically number of molecules are there, but in one molecule this contains 10 electrons and 10 proton. Correct? So that means how much charge will be there? Positive or negative? Positive or negative charge in a cup. Number of molecules are your 250 upon 18 into 6.02 into 10 raised to 23. And in one molecule, these are number of molecules into 10 electron or proton. And what is the charge on one electron or proton? That is 1.6 into 10 raised to minus 19. Correct. If you calculate this, then this will come as 1.34 into 10 raised to 7. So, in a cup of water, we have assumed that in a cup of water, 250 gram of water is there, and that will contain this much amount of either positive charge or negative charge. Correct? Let us go further. Coulomb's law, we have seen, we have studied Coulomb's law. Correct? So, there is one example regarding Coulomb's law is also there. Coulomb's law for electrostatic force between 2 points, charges, and Newton's gravitational force between two stationary point masses both have inverse square law dependence on the distance between the charges and masses respectively. Naturally, what is Coulomb's law? That is your FC, you can say. That is K Q1 Q2 upon R square, correct? Or we can write it as, if we into, suppose there are two electrons, then it is basically K E square upon R square. And what is gravitational law? G M1 M2, or we can write, suppose this is between one proton and one इलेक्ट्रॉन, अगर इसको हम करें तो ये क्या हो जाएगा, प्रोटॉन मास एंड electron mass divided by r square. R is the distance between them, which we have taken same in both the cases. So this is your, due to gravitational attraction will be there, and this is due to proton and electron. Of course, both are unlike charges, so attractive force will be there. Correct? So now let us see further one. Compare the strength of these forces by determining the ratio of their magnitude. Now, if we compare these two magnitude wise, then here E square upon K, value of K is nothing but 4 pi epsilon 0. Then of course G will be there, then MP into MP. Correct. You know the charge, you know the mass of the proton, or you know the mass of the electron. If you calculate, you will know the value of G also. This, if you calculate this, then it will come as 2.4 into 10 raised to 39. Correct? Now just see, electric force is very and very big in comparison to gravitational force. So this is the comparison for an electron and proton. We have seen for an electron and proton, this is the coming because we have taken one electron and proton. For two protons, if we take from for two proton, of course, this is the, you can say this one. For two proton, E will be same, but Here, of course, we can write it as Fc upon Fg will be nothing but E square upon 4 pi epsilon 0, then G MP into MP, correct? And this will be 1.3 into 10 raised to 36, correct? So between two protons, this much, this is the ratio of repulsion of electric forces between them and attractive forces between them, correct? Now, what estimate the acceleration of the electron and proton due to electric force of their mutual attraction when they are 1 angstrom apart, correct? When they are 1 angstrom apart. So, let us see what is the electric force. Electric force is nothing but K E square upon R square. This you can write it as 9 into 10 raised to 9 into 1.6 into 10 raised to minus 19 square divided by distance between them is basically 1 angstrom. 1 angstrom is 10 raised to minus 10 whole square. This comes as 2.3 into 10 raised to minus 8, correct? So what will be the acceleration? Force upon m, correct? So acceleration of basically electron, because proton is basically you are bounded in nucleus. Acceleration of, if we see electron, then 2.3 into 10 raised to 8 divided by what is the mass of the electron into 10 raised to minus 31 kg. And this is basically Newton. This will come as 2.5 into 10 raised to 22 meter per second square. Now this compare this thing with your acceleration due to gravity. It is much more than this thing. So if we compare this, the effect of gravitational field is negligible, correct? So gravitational field is negligible when there is a motion of electrons, correct? So Coulombic forces, they have, they are very effective in case of small bodies like electron and proton. Of course, value of acceleration of the proton, if you compare, then this also you can compare 2.3 into 10 raised to minus 8. This thing 1.67 into 10 raised to minus 27. This is your ma mass of the proton, and it is also very large value. Correct. Now, there is one more thing in this question, that these two things are dimensional करना चाहिए. This ratio is dimension less. Of course, that will be dimension less only because it is the ratio of two forces. Correct? It is a dimensionless parameter. Dimensionless parameter is what? Basically, this parameter, which we have seen this thing. Correct? So this was basically the example which your NCRT book is, in which NCRT book is there. Now we will go to the next, this thing. It says a charged metallic sphere A. This is a charged metallic sphere suspended by a hollow thread. Another charged metallic sphere. This thing is it. This is also a charged metallic sphere held by an insulating this thing. Okay, insulating hand is brought close to A such that the distance between them and the center is this. So here you are bringing these two, and distance between them is 10 centimeter is given. Correct. Then what is say? The resulting repulsion of A is noted. Correct. So means the, suppose here the charge is Q1, here the charge is Q2. So what will be the repulsion? Repulsion will be K Q1 Q2 upon 10 centimeter is there, means zero point 0.1 square. Correct. Now it further says spheres A and B are touched by an uncharged sphere C and D respectively. B and C are then removed and D is brought to the 5 centimeter. Correct. What is the expected repulsion of A on this, on the basis of Coulomb's law? Is sphere A and C and sphere B and D have identical sizes. Ignore sizes of A and B in comparison. Okay. So now when these are touched, then what will happen? When these two are touched, then it, this is a uncharged, this is charged. So what will happen? It will have half the charge. In this case also, this is uncharged and this is charged. If you touch them, this will also become. Now what is the force? Suppose F dash is the force now, then Q1 by 2, Q2 by 2 divided by 0.05 square. Correct. Or we can write it as, but for simplicity, this is R square, where R is 0.01 meter. And here, basically, it is R by 2, R dash. So we can write it as K Q1 Q2 upon 4 R by 2 square, or we see K Q1 Q2 upon R square. That means this is your F only. So there is no change in the repulsive force between the two A and B. So this is how you can do this. Correct. This is a question of Coulomb's law are placed at a distance 0.5 meter in vacuum. So very simple question. K Q1 Q2 upon R square, and that is 9 into 10 raised to 9 into 2 into 10 raised to minus 6 coulomb, 3 into 10 raised to minus 6 coulomb divided by 0.5 square. Correct. So if you calculate this, this will come as 0.216 Newton, correct? If you want to draw the figure, there is one Q1, Q2 is there, R is the distance that is given as 0.5 meter, and there will be a repulsive force because both the forces are positive, and this is your value of the forces basically. Correct? I hope this is clear. Now we have seen कि Coulomb's law between two charges, whether they are positive charges or they are negative charges, opposite charges, and how to find the force between them. We have calculated all those things. But there are suppose multiple of charges, correct? So multiple of charges means suppose how you are going to find out. Suppose you have Q1, or you can take it as a Q2, take it as Q1. Another charge you can take as Q3. Now, if I ask you how to find the force on Q1 due to Q2 and Q3, correct? So, here comes the principle of superposition of forces. Means we have to find out the forces due to the other charges, and we will take the vectorial sum of the forces, correct? So let us see the theoretical part of it. What its definition says: the net electric force on a charge due to a number of other charges is equal to the vector sum of the forces exerted by exerted on it by each force taken individually, correct? Each charge produces force independently and total force is obtained by vector addition. So this is the basically formula, means F1, F2, F3, these are the forces acting on the that charge, and on that charge, if you want to find the force, is the vectorial sum of this. Look, it will be clear. Suppose if we calculate like this, suppose you have, let us see, this is your origin, this is the position vector of Q2, this is the position vector of Q3, and this is the position vector of R1. We have to find out the force on Q1 due to Q2 and Q3. So what we will do, as we have seen, due to Q2, there will be a force on Q1 like this, and this will be F12. And due to Q3, there will be a force like this on Q1. We can designate is F13. Then, what is the force on Q1? It will be basically the vector sum of this. This will be the, if we denote F1, that means F1 is nothing but F1 3 plus F1 2, like that. If you have multiple of charges, here you already have studied how to find the resultant of vectors where they are, when they are inclined at some angle, basically. Correct? Just for short, let us see. Suppose you have a vector A, and if you are attaching vector B, then what is the resultant? Tail of this and head of this. And suppose this is your R, then it is basically this plus this. Correct? We can find out this way also. You take A, this is your B, and by parallelogram method, this is your C. If vectors are inclined at theta degree, then you have seen this formula also. R is nothing but root A square plus B square plus 2AB cos theta. This is the magnitude of your resultant. So these things you have studied in your class 11th. So I am not going into those details. Main thing is this, here, if you see what is F12, F12 is nothing but K Q1 Q2 upon R12 का whole square, and this is R12 unit vector. Likewise, F13 K Q1 Q3 upon R13 whole square, and this unit vector of R13. What are R12 and R13? If you see, then these vectors, these your vectors, your R12, and these vectors, your R13. Vectorially. Correct? Unit vector of R12 is nothing but basically in this direction only, in the direction of R12. So this is called the principle of superposition. So if you have a number of charges surrounding Q1, then you have to find out F12 plus F12, 13 due to force on 1 due to 3, force on 1 due to 4, like that. So this is the principle of superposition, which is the vector sum of this thing. Correct? Now let us move further. Based on this superposition, there is an example in your NCERT book, and that is like this, which is on your screen. Here we have There are three charges Q1, Q2, Q3. So this is your Q1, this is your Q2, and this is your Q3. Each are equal to Q only, correct? And it is a equilateral triangle of side L. What is the force on the charge Q with the same sign as Q placed at centroid of the triangle? So this is the centroid O where charge Q is placed. Naturally, they have marked the forces in the figure. You will see due to Q1, this F1 repulsive force is there. Due to Q2, F2 repulsive force is there. And due to Q3, this F3 repulsive force is there. Correct? Now, what is the distance R? R is basically this AO. And what is AO? AO is nothing but 2 by 3 of AD. And what is AD? AD is nothing but AC cos 30 degree. Correct? Because this is what? This is equilateral triangle, this is your 30 degree. So means 2 by 3 into L into cos 33 is root 3 by 2. And if you calculate this, then this will be L by root 3. This is your AD basically. Or you can say this is the R basically we have to put. What are forces F1, F2, F3? Since AO is equal to BO equal to CO, correct? So AO and that is equal to L by root 3. So all these forces, since this is Q, this is Q, this is Q, so all these forces will also be equal. F1 will be equal to F2 will be equal to F3 and this will be equal to K Q Q upon L by root 3 whole square. There is no problem in this. So we have seen this F1 equal to F2 equal to F3 and we can say it is F. Now this geometrically if you see these three forces are there F, F and F and if we resolve resultant then suppose this is F dash, F dash we can write it here, F dash is nothing but 2F cos 60 degree because all these three forces are at 120 degree each other. So this angle is nothing but 60 degree. That means 2 into F into 1 by 2 means F only. So this is your F only, correct? So this F and this F will counterbalance each other. Ultimately, the force will be 0 on capital Q due to other charges. Correct? I hope you understood this. Let us see this question. Consider the charges Q, Q minus Q placed at the vertices of a equilateral triangle. Correct? What is the force on each charge? So since so magnitude of the forces is nothing but K Q1, or you can say Q square upon L square. This is the magnitude of this F. What is this F? This is your F. This is your F, because minus Q and Q both will be attractive, correct? So naturally, what is the resultant force F3 means on this is your Q3. Q3, Q3, what is the resultant F3? F3 is nothing but 2F cos 30 degree, and that is nothing but root 3F, or you can say root 3 into K Q square upon L square. Likewise, what is F1? F1 basically this is your F magnitude wise, this is your F, correct? So your F1 will be nothing but 2F cos 60 degree, correct? Cos 60 degree is your 1 by 2, that is F. Means this is your F only, and that is given by K Q square upon L square magnitude. Similarly, this will also be F and K Q square upon L square, correct? So if you see, these are the basically forces on individual charges, correct? So if you take the vectorial sum of F1 plus F2 plus F3, then geometrically, if you see, this is your F, this is your F, correct? This is charge on Q1, then this is charge on Q2, and of course, this is your F, that is charge on 3. This angle is 60 degree, and this is basically root 3F, correct? So 2F, what is the resultant of this? This resultant is, suppose F dash is nothing but 2F cos 30 degree, and nothing but this is root 3F. So root 3F and root 3F, they will balance out each other. Again, this will be equal to 0. Correct? So this is the solution of your example. Solution is given in the book also. You can see that, but it is very simple. Correct? Let us say what is electric field now. Suppose some charge is there, Q. It has an area of influence like this. Now, suppose if we bring a Q0 charge towards capital Q, Suppose this is at infinity, naturally it will not be experiencing any force because this charge will have a limited area of influence. But once this Q0 charge comes in the influence of Q, then it will experience a force that is K Q Q0 upon R square. And what is this? This is basically R is the distance. Now, Q0 will also have its own field so that there should not be interaction between the field of capital Q with the field of Q0. What we can make, we can take Q0 is very small. Then this electric field is defined as K, or you can say electric field at a distance R is defined as F upon Q0, and this we can write it as K Q upon R0. What is this? This is electric field at a distance R from Q. Correct? So, means suppose you have a Q0 charge here, then we can always say that at a distance of R, at a distance of R, here, this will be the electric field, and it is the value of this is Q upon R square, and direction of the electric field is the same as what this force was having, this force. Correct? So direction of this electric field is same as what this force means in the direction of R, or we can write it as unit vector of R. So now let us see what is the definition. Electric field at a point is the force experienced by a unit positive test charge placed at that point. Means we have seen at a distance of R, electric field is this. Then suppose if we place a Q0 test charge here, then how much force it will experience? It will experience a force of E into Q0, or K Q0 upon R square. Correct? So this is, so if you know the electric field at any point, then if you bring that any charge on that point, it will experience a force. Correct? And the direction of the force is nothing but, as we have seen in Coulomb's law. If there are like charges, then of course direction will be repulsion. Unlike charges are there, then direction will be attractive. Correct? So Now we can review this mathematical expressions we have seen, electric field due to point charge we have seen, nature of electric field, of course, it's a vector quantity, and direction is away from for the positive charge, of course, because it will be repulsive, and towards negative charge. Electric field lines basically they start from the positive and at negative, that we will see in when we will draw the electric field lines. They never intersect. Of course, electric field line tangent to the electric field will be the direction of the electric field. So there cannot be two directions being tangent. Closer lines indicate stronger field. If the lines are closer, means stronger field. Okay, so what is Figless signal here? Explains the force without contact. Yes, because due to this field, the charges are experiencing the repulsive as well as attractive force without any contact. Helps calculate using the F. If you know the electric field at any point, if you bring the Q charge on that point, then you can find out the force experienced by the charge Q. Describes the region of influence around the charge, hence in visualization using it. This is basically written. And electric field lines, as you have seen, we can see the definition. Electric field lines are imaginary lines drawn in an electric field such that tangent at any point gives the direction of the electric field and density of the line depend on the strength of the field. Correct. So if there is a positive charge, then how will be the electric field lines? Electric field lines will be, in case of positive charge, this is away from the in all the directions. Correct. Now you know, suppose this charge is Q. If you place a charge here, Q0, and distance between this, you can take this point as P, distance between these, then naturally this Q0 will experience a force like this in the direction of the electric field line. And you already know what will be the value. Value will be Q0 upon R square. Why? Because here the electric field EP means at point P, electric field will be K Q upon R square. So F is nothing but Q into EP. Correct? Very simple to understand. Now, in case of negative charge is there, sorry, in case of negative charge, then the electric field line nature of the electric field towards the charge like this, because if you place any charge Q, so here it is positive charge, here it is negative charge, opposite charges are there. So electric field, direction of the electric field here in this case will be like this, E. And naturally, force will also in the same direction because force is nothing but Q into E. I hope this is clear. Correct? Electric field you can define like this also. E divided by Q, limit Q approaches to zero means force divided by the charge Q approaches to zero means, so that the influence of Q you should not consider. Okay? Or electric field is a 4 per unit area. Correct. Now, here you have to see one more thing. Suppose there are Q1 charge, here Q2 charge, and here Q3 charge. There are multiple charges are there. And if I ask you what is the electric field due to these charges on this point, then what you will do? You can again the same way superposition. This is the electric field due to 1. This is the electric field due to 2. This I am taking. These are positive charges, so electric field direction will be away from the charge. And this is the electric field due to. So you have elect three E1, E2, E3 electric fields at this point. This is suppose R1, this is R2, this is R3. Correct. Then what will be the electric field at P? Electric field at P will be the vectorial sum of E1 plus E2 plus E3, like we have seen in superposition of forces. Correct. Or it can be written as K Q1 upon R1 square plus K Q2 upon R2 square plus K Q3 upon R3 square. Correct. And this is EP. Of course, vectorially, if you see, then you have to take the R1 unit vector, R2 unit vector, and R3 unit vector. Unit vector also you have to see. So, this is how you can find out the electric field at any point due to the multiple charges. Correct. Properties we can once more see. Start from the positive charge and negative charge means, suppose you have positive and negative charges. Correct. Then you can draw like this electric field lines. This is positive charge. This is negative charge. Then electric field lines will be like this. They will emanate from positive charge. They will end on the negative charge. Correct. Then like this, you can, this is basically your positive and this is negative. And suppose you have both positive, both positive sign mean they will repel. In that case, you can make like this. Like this, you can make the electric field lines. Correct. Now, suppose you have parallel plates. These are metallic parallel plates. Here you have positive charge. Here you have negative charge. Then how will be the electric field lines? Electric field lines will be starting from positive charge. So this is the idea. Generally, electric field lines, they go away from the positive charge and stop at negative charge. Correct? Now let us see. There is one question. Again, we will let us solve this question. Correct? Let us see what this question says. An electron falls through a distance of 1.5 centimeter in a uniform electric field of magnitude epsilon. The direction of field is reversed, keeping its magnitude unchanged, and a proton falls through the same distance. Compute the time of fall in each case. Contrast the situation with that of free fall under gravity. Correct. So let us see figure A. In this figure, this plate is negative and this plate is positive. Now this is electron. Electron, naturally, electron is a negatively charged particle. So it will be repelled by the negative plate and it will be attracted by the positive plate. Correct? Here the field direction, this is the field direction from positive to, but electrons being negative, it will be moving opposite to the electric field direction because it will be attracted to the positive. Yes. Now, what will be the force electron will be experiencing, that is E into E, and what will be the acceleration of the electron, that is E into E, because F is equal to Q into E. Okay, don't forget this. This is the acceleration due. With this acceleration, this will move downwards. Correct. So it says falls through a distance 1.5 centimeters. So we have a S is equal to ut plus half at square. Here, since it is falling, though this will be zero, initial velocity will be zero. So what is the basically time? Time is nothing but 2s upon a. Here 2s upon a, we can e, or we can say this will be equal to 2s upon e e into m e. This is the time which will be taken by the electron in moving a distance of 1.5 centimeter. If you put all these values, all the values are there, they given, correct? This distance 1.5 centimeter, me, mass of the electron, electric field is already given in the question, and charge on the electron is here. So T, if you put all these values, T will be 2.9 into 10 raised to minus 9 second. This much time electron will take moving this distance 1.5 centimeter. Correct. Now, in the figure B, now electric field is downward. It is reversed. That means this is at positive plate, this is at negative plate. Now positive reverse keeping a proton now protons falls. Proton naturally it is a positively charged particle. It will be attracted towards negative plate. So what will be the acceleration of proton in the similar way? E upon, correct? And in the similar way, what is this is your time for electron, then time for proton also. We can find out the in the similar way. So TP, if you put the value, it will be 1.3 into 10 raised to minus 7. Correct. Now, proton is a heavier particle. Correct. Proton is a heavier particle and it is taking more time to fall through the same distance. Correct. Proton is a heavier particle. It is taking more time than electron, first of all. That means here the time is dependent on the mass, whereas in gravity, time is mass independent. Correct? Mass independent. Now, so this is the time, this thing. Compute the time of a contrast with the situation that of a free fall under gravity. Correct? Now, let us see another question. 2-point charges Q1 and Q2 of magnitude 10 raised to minus 8 Coulomb and minus 10 raised to are respectively placed at 0.1 meter apart. Correct? So these are the charges. Calculate the electric field at a point A, B, and C. So A is this, A, B, B is this, and C. Correct? So let us find out first A. At A you see one charge is here Q2, another charge is Q1. Correct? So due to Q1, it will have a direction of electric field like this, and due to Q2, since it is a minus charge, again here the electric field will be in this direction only. Correct? So EA, we can say it is the combination of EA1 and plus EA2. Electric field at A due to 1 and electric field at A due to 2. And what is due to 1? That is K. What is the Q1 upon 0.05 square, because A and Q1 distance is 0.05, and here it will be K Q2. Here also the distance is 0.05 square. Q1 and Q2, you know, 10 raised to minus 8 Coulomb. Correct. Now, since we have taken the direction of this, that's why we have put plus here. That means you have to just put K 0.05, this thing here, 10 raised to minus 8 plus 10 raised to minus 8. Mind it, because minus sign we are not considering because we have already taken the direction because of the minus charge. Correct? And EA, what is the direction of EA? It is towards the right. You can calculate this thing. Then let us see what about B. B, you see, there will be one due to Q1, repulsive, this thing will be there. And this is naturally due to Q2, it will be like this. Correct? So it will be the vectorial sum of this thing. Means EB will be EB1 minus EB2. And here again, Q is 10 raised to minus 8 divided by, I think this distance is this thing only, and K 10 raised to minus 8. Here, this distance is basically 1.05. Sorry, 0.05. 15 square. Correct. So here I have put minus because due to Q1 it is on left side direction is there. Due to Q2 it is on the right direction. That's why there will be a difference of this, and this you can calculate. Then let us see, due to these charges, what will be the electric field at C. So due to Q1, this E1 C is there, and E1 C is nothing but it is K Q1, whatever this thing is there, and zero point 0.1 whole square. And then it is basically minus charge is there, so electric field direction will be towards the Q2, and this is your K Q2 0.1. Correct. Now we have to vectorially we have to find the resultant of this EC. So EC will be nothing but E C1 cos pi by 3, because if the angle is pi by 3, then E2C cos pi by 3, and even C1, this thing you already know, so you can calculate. So this is how we can, and what will be the direction? Direction will be towards the right. Correct. Pi by 3 angle, how it has come? You can always see that what is this angle? This is 0.1, and naturally it is all 60 degree. So what is this degree? This will be basically 120 degree. So half the angle will be 60 degree. I hope there is no problem. Correct. See the figure, understand the things, keep your geometry very strong, because these questions are very easy, and we should not spend that time in understanding the problem and doing it. You have to be very quick and accurate. Answer should not be wrong. Correct. I have given you the idea how you want to do it. For calculations. You can always see the book, or you can do the calculations yourself and see the answers match with the book. Correct. Now let us see another topic in this chapter, and that is electric flux. Electric flux means, suppose you have a electric field lines like this. And you have an area perpendicular to the line of the electric field lines. Then these electric field lines, they are passing through this area. Correct. And this is called basically flux. So Electric flux is the measure of total number of electric field lines passing through a given surface, or you can say area. In simple words, it represents how much electric field is flowing through a surface. Correct? Now, this area can be tilted also. It need not be perpendicular to the field lines. Correct? So, suppose you have a this area is your delta S. Correct? So, one thing is your your area is completely perpendicular to this. Now, suppose this is the area perpendicular to this, then what will be its area vector? Area vector will be like this, normal. This is your area. This is your electric field. Now, suppose your area is like this. That means normal to the area, that is area vector. This is your ds. And electric field line, it is making an angle theta. Then, what is phi? Phi is defined. That is, phi is what? It is electric flux. This is defined as the dot product of or E delta S cos theta. Whereas where theta is the angle between the normal and the electric field line. Correct? Now, if you see delta S cos theta, this is the now in case of tilted area, this is the area which is perpendicular to electric field lines, means exposed to the electric field lines. Correct? So when theta is your 90 degree, then here when theta is your 0, then your area is perpendicular to electric field lines. When theta is your this thing, means theta means 0 means area vector is this thing. So area vector and E both are parallel to each other. Correct? When area vector and E they are perpendicular, correct? Then basically your area becomes parallel to electric field lines. And naturally, in that case, your flux will be 0 because it is parallel to electric field lines, means no electric field lines is passing through the area. It is a basically scalar quantity. It is the SI unit of flux, and electric flux measures electric flux through a surface depends on the field area and orientation, of course. So this is the electric flux. Electric flux basically it is the measure of electric field lines passing through some surface. Means how many lines are passing. Number of lines are more means flux is more. Number of lines are less means flux is less. So this is a measure of current. Correct? So this. Now, suppose, let us see, electric field is given in this question as E is equal to 5 into 10 raised to 3 Newton per coulomb. As you see the unit E is nothing but F upon Q. So Newton per coulomb acts on a surface of side 2 meter. So area is basically your 2 square, it is 4 meter square. Surface is inclined at an angle 60 degree with the electric field. Now here, basically electric field direction is this. Your surface is inclined. So what about the normal to the area? This is the area vector and this is the electric field. Then what will be this angle? This will be 30 degree. So naturally, your flux will be E A cos theta, or you can say 5 into 10 raised to 3 into area is 4 into cos 30 degree. So this is how you can calculate the flux passing through that area. This is the part of the chapter, that's why proceed. Correct? Now, now let us see what is a electric dipole. So before you is the definition of electric dipole. An electric dipole is a system of two equal and opposite charges separated by a small distance. In simple words, a pair of equal and opposite charges separated by a finite distance. Suppose you have a positive Q charge, another charge is equal and opposite charge, and it is separated by a very small distance, that is d. Then what is dipole moment? Dipole moment is given by Q into d. Now it is a vector quantity. So this dipole is denoted as P equal to Q into d, and this is a vector quantity, and this vector is, direction of this vector is from minus to plus. So this will be towards the right side. This will be the direction of the dipole moment. Correct? So dipole moment is this thing. Dipole is basically electrically neutral because equal and opposite charges are there. So it is basically electrically neutral. It produces electric field that we will see. It is a vector quantity, I told you. Correct? Now, let us see the electric field due to dipole. There are two types of electric fields, on the axial axis and another is on the equatorial axis. So let us drive the formula for axial electric field and equatorial electric field. So for axial electric field, Suppose you have a dipole and it is separated by a distance 2a. And this is the midpoint of the dipole. Now we can take axial electric field means this is the axis of the dipole. We can take this P point and we have to find out direction of the dipole will be like this. We have to find out what is the electric field at P due to this dipole. So if you see from this positive charge, suppose this is r distance, then what is this distance? This distance is r minus a. And what is this distance? R plus a. Correct? Now, electric field due to plus charge at P is nothing but K Q upon R minus a square. What will be the direction of this electric field? Direction of this electric field will be like this. You go away from, it is due to the plus charge, so it will be away from the charge at P. What about electric field due to minus charge? That will be K Q upon R plus a, this thing. Direction of this electric field will be in this direction towards the, because it is a minus charge. From this, you can see E plus P is greater than E minus P. So what is the resulting electric field at P due to the dipole? So this will be KQ 1 minus 1 upon R plus N, because both are up in opposite direction. So the difference of this electric field will be at point P. Correct? If you simplify this, then you can see this is equal to 4 AR upon R square plus A square now. Since R is quite larger than A, then we can write it as KQ 4AR divided by, here it will be minus R to the power 4, 1 minus A square upon R square whole square. Or this can be simply, since R is quite greater than A, then this factor, it will be very less. So we can write this as KQ 4Q sorry, 4 A upon R Q. What is P here? P is basically Q into 2A. That is the dipole moment. So this formula can be written as K 2P upon RQ. Correct? Where K is 1 upon 4 pi epsilon. What will be the direction of this electric field? We have seen due to plus charge it is more. So direction of the electric field is in the direction of P only, towards the right. I hope this is clear. Correct? Here also, this is K 2P upon R cube. This is what we have derived here. Now, we will see electric field due to dipole equatorial. Correct? Equatorial means suppose you have a this is the dipole 2A, this is the midpoint, and we have to find out the electric field at P due to this dipole. And this PO, you can say it is at the perpendicular bisector of the dipole. So if you see, this is the minus charge. So electric field will be in this direction due to minus charge. This is your E minus Q, and due to the plus charge, this will be basically E plus Q. Both will be equal because these distances are equal. This is suppose this is your R. At a R distance, we have to find out the electric field at P. This is A. So what is this? This is basically is nothing but root R square plus A square, and EQ and E minus Q will be equal because both this they are at the same distance. Now if we find out the resultant of this, it will be like this. Correct? So let us, what is E plus Q due to plus Q? What is the field at P? That is KQ upon R square plus A square. Correct? And that is KQ upon R square plus A square. Just see, both the fields are equal. Correct? So what is the resultant? EP. The resultant of this will be minus E plus Q P cos theta plus E minus Q P cos theta. Correct. What is cos theta? Cos theta is nothing but this is the angle. Correct. And what is this cos theta? Let us find out what is this cos theta. Cos theta is nothing but, if you see, this is your theta, and this will also be theta. And cos theta is nothing but your A upon root R square plus A square. Correct. So if you put this value EP minus, here it will come as KQ A upon R square plus A square 3/2. Now if R is quite larger than A, we can write this formula as KQ A upon R cube 1 plus A square upon R square 3/2. So this factor will be 0, and our formula is after approximation, that is K. Now what is P? P is basically Q into 2A. So here we can write it as K P upon R cube. Here minus sign is because our direction of P is towards the right, but electric field at P is towards the left. So P direction of the P is towards the right. So it is anti-parallel to the direction of the dipole moment. So here again, electric field is opposite to the direction of the dipole moment. Correct? E is proportional to, of course, field decreases rapidly with duration. Axial field is twice equatorial field. You have seen axial, which we have found out earlier, that is K 2P upon R cube, and A equatorial, that is K P upon R cube. Correct? So this is how you can find out the electric field at the axial point and at the equatorial point due to the dipole. Correct? Theoretically, if we see why this dipole moment we study, you must have seen many molecules center of positive and negative charges coincide, and in where the center of positive and negative charges they coincide, then dipole moment is 0. So there are non-polar molecules like CO2 and CH4. Correct. But when an external electric field is applied, even non-polar molecules develop an induced dipole moment. Correct. So you see the molecular state. Molecular state means there are certain molecules which are non-polar, and there are certain which are natural like H2O. It is a polar molecule. correct? And their electric behavior can be studied once we study about the dipole moment, correct? Now, let us go further. This is one question which has been given in your NCERT book. Let us see how we can do it. There are two charges are placed 5 mm apart. Determine the electric field at a point P on the axis of the dipole 15 centimeter away from the center on the side of the positive charge as shown, and a point Q 15 on the line passing through the normal to the axis. So it is a total formula based question. A part, you have to apply the formula of axial electric field which we have. And what is that? 2, no, not 2, basically it is K 2 P upon R cube. Here, K you know 9 into 10 raised to 9. P we have been given, that is 10 microcoulomb is 10 raised to minus 6 into distance to A. Distance is given between the 5 mm apart. So 5 into 10 raised to minus 3. This is the value of P you have to put. And what is the value of R? R is given 15 centimeter away from the center. So R is from the center only. Correct? I think we have put from the center. Let us just check when we drive the formula. No, R is here, R is from the center. That's why it is R minus A and R plus A, correct? R is given as 15 centimeter, means 15 into 10 raised to minus 2. Due to this, just put the values, you can find out the electric field at B, at P. Now, B part is equatorial field. Equatorial is nothing but K P upon R cube. Here, P is same, but R is also same, 15 centimeter from the O on the line passing through the. So, all these values you can put here, it will come half of its value. This is how you can do this question. Correct? Now, there can be instances where your electric field or where your dipole is there in the uniform electric field, like this. Suppose your dipole is there. Here minus Q is there, plus Q is there, and we have an electric field direction like this. This is the external electric field. Your dipole is placed in an external electric field. Suppose this is the center point, and this is the vertical line. Correct. So this is the direction of the electric field, and this is the direction of the dipole moment. Suppose they have an angle of theta. Now, if your dipole is placed in an electric field, then what will happen? This will experience, this positive charge will experience a force like this, and this negative charge will experience a force like this. Correct? Whenever there is some charge in the electric field, the force is what? Q into E. Correct? So, since both the forces are equal, so net force on the dipole is zero. But there is, of course, if you see, what is this distance? Suppose this is your A and A. 2A distance is there. Then what is this distance? 2A sine theta. Correct? This is 2A sine theta. So it will have a torque. Now this force, one is upward, another one is, it will try to rotate the dipole. So what will be the value of the torque? That will be Q into E into 2A sine theta. Your P is basically Q into 2A. That means this is P E sine theta, or we can write it as this is the cross product of dipole moment into electric field. Correct? So here, if you see, when theta is 90 degree, when theta is 90 degree, what is happening? Your P is like this, and your E is, so this is the position where it will experience a maximum torque. And when theta is 0, means it is in the, P is in the direction of the electric field. Then when your dipole moment is aligned along the electric field, that means your torque will be 0. It will not experience any torque, because suppose electric field is like this and your dipole is like this. Then what are the forces? This will be F QE and this will be FQE. Line of action of the force is same, correct? So naturally there is no torque, or there is no tendency of rotating this torque. These forces, they cannot rotate the torque or dipole basically. I hope it is clear to you, correct? So 0 degree, no torque, it is a stable equilibrium. Of course, it will try to remain in this position. When 90 degree, the torque is maximum. Then 180 degree, it is in 180 degree means E is like this and P is your like this. Correct. Potential energy we will see in the next chapter. Correct. So let us go further. Continuous charge distribution. Charge distribution. We have seen so far the isolated charges Q1, Q2, Q3 like that. But there may be a reason, maybe a situation where suppose some dot is there of length L and you have put the total charge on this as Q, then linear charge density, lambda, linear charge distribution or linear charge density, what will be this? This is basically Q upon L, correct? Because charge is continuous on the rod. There can be a situation where suppose there is a metallic sphere and charge is distributed on its surface. Its radius is suppose R. Then suppose if you have total charge as Q, then what is the surface charge density? Surface charge density is denoted by sigma, and that will be equal to du Q upon it is distributed on the surface. So, what is the surface area of the this thing? Q upon pi r. So, you may be given lambda, you may be given sigma, and there is another volume charge density. Suppose you have an sphere, non-metallic, and all its volume charge is distributed, then volume charge density is denoted by rho. And suppose this total charge is Q, then Q is nothing but, suppose its radius is R, 4 by 3 pi R cube. Correct. So instead of having isolated, we are going to deal with the linear charge density, surface charge density, and volume charge density also in our chapter. Correct? Or mathematically, if you see what is total charge is nothing but it is the integral of smaller charge which is on the surface or in the volume, whatever it is. Correct? Now, next thing is very important thing. What is Gauss law? Gauss law says total electric flux through a closed surface equal to this is basically 1 upon epsilon 0 times the charge enclosed inside the surface. Now, suppose you have a Q charge. You, as you have seen, its area of influence will be These are the electric field lines. Suppose if we make a surface, then through this surface, all the electric field line coming out from the plus Q charge, they will pass through. If we make another surface, wider surface, oh sorry, in this case also, all the electric lines, they will pass through. Means whether the surface is this, whether the surface is this, the flux is same. Electric lines, we have seen number of electric lines passing through a surface. They are called electric flux. Correct? So Gauss law states that total electric flux, it is equal to Q divided by epsilon. Correct? Earlier we have seen this formula as V into ds, and naturally this will become. So this is the basically Gauss law, that if any charge is enclosed through a surface, then total electric flux will be equal to Q upon epsilon naught. There should not be any doubt about it. Now, electric field, if you want to find out, suppose in this figure, there is a point P. If you want to find out the electric field, which is R distance away from this. So, with blue color, we have make a sphere. This is called basically Gaussian surface. Gaussian surface is a 3D surface. You have to make the Gaussian surface such a way that you enclose that charge. Then, as per Gaussian surface, your this phi is nothing but Q upon epsilon 0, and that is equal to E into A surface area. Surface area at R, what is this? 4 pi R square. That means electric field at R, you can always find out Q upon 4 pi epsilon 0 R square. This is what basically you have seen whenever some charge Q is there, then what is the electric field at this? Electric field is nothing but Q upon 4 pi epsilon 0 R square. So this is through Gauss law also you can find out the electric field as you have seen here. Correct? Suppose if I say you have an sphere or you have a shell, you have a shell, now you want to find out at P, this metallic shell is there. You want to find out, suppose Q charge is placed at the center of the shell. Then you want to find out the electric field at P. Then what you have to do is, what is the area, radius of the cell? That is R. Correct? Assume this surface as a Gaussian surface, then E into 4 pi r square is nothing but q upon epsilon 0, or electric field at P is nothing but q upon epsilon 0 4 pi r square. Correct? So this is how you can find out the electric fields. This thing. So Gauss law, what are the salient features? This is applicable to closed surfaces only. Gaussian surface. Open surface you do not draw. Depends only on the enclosed charges. Electric flux depends only on the on the charge inside the surface. Charges outside the surface have no effect. Independent of shape and size, flux is same regardless of the shape or size. Means suppose Q charge is there, you make a spherical Gaussian surface, or any other surface, since all the electric field lines will be passing through this, the flux will be nothing but Q is equal to Q upon epsilon 0. Suppose you have a cube and at the center of the cube, at the center of the cube, Q charge is there, then how much flux is passing through this cube is nothing but Q upon epsilon 0. And suppose if you are asked that what is the flux through one side, since it is a cube, all the sides are equal, one face you can say. How much flux, suppose, is there passing through one face? There are 6 faces. So naturally it will become Q upon 6 epsilon 0. Sorry, this is 5 through one face. Correct? So Gaussian, you can draw the Gaussian surface with your convenience, and you can find out the electric field or electric flux, whatever is asked in the questions. Correct? Here the similar question is there. Electric field components are Ex. So let us see this question. This question says your Ex is alpha A 1 by 2. Alpha is given as 800 Newton per Coulomb meter 1 by 2. Correct? And A is also given. A is basically for here alpha. This is x square. A is given as meter. Correct? So we have to find out the flux through the cube. What is flux? Flux is nothing but E into A. Flux at the left side entering into the cube will be E. What is E? Alpha. Here the distance of x is A 1 by 2 into A cube. What is R? It is the flux going outside the cube, alpha, but here x value is 2A into A square. So Net flux inside the cube is nothing but al alpha. This is A 5 by 2 root minus 1. Correct? This is your 2. It will become 5 by 2. Amazing. So all these things, you can find out. This will come as 1.05 Newton meter square upon Coulomb. Another part is also there, the charge within the cube. So flux is nothing but Q upon epsilon 0, or Q is nothing but phi into epsilon 0, and Q is nothing but 105. Epsilon value of epsilon is nothing but into 10 raised to minus 12 Coulomb. And then that means inside the charge is nothing but this. Correct? So this is how you can solve this question. Now, let us go. There is one more question is there. We have electric field uniform is positive, this thing, this thing, this thing. A right circular cylinder of length itna has center axis around it. What is the net outward? So means there is a first of all, let us draw the cylinder. This is the now as per question here E is in this direction. Of course, area vector will also be in this direction. Correct? Here, as per question, E is in this direction, and area vector is also naturally it is outward. The radius is here given as 5 centimeter. Correct? And this distance is minus 10 centimeter. This is plus 10 centimeter. So basically, this is complete 20 centimeter. Correct? So E is basically your 200I when X is greater than 0. E is basically minus 200I when X is less than 0. This is what is given actually. Now what is the net outward flux through each flat face? Correct. Now, flat face is perpendicular to electric field, so you will have a flux moving through this. The surface here the radius or the area vector is perpendicular to E, though there won't be any flux out of this. So only so let us see what is the flux coming out through the left circular face, that is E into delta S, and that will be equal to 200 into 0.05 square. Correct? And what is right E into delta S? This will also be equal to 200 into 0.05 square. Correct. So what is the net outward flux through each flat face? So this is the net outward through left face and through right face. What is the flux through the side of the cylinder? Side of the cylinder, I told you, area vector is perpendicular to the E. Since E and S are dot product, so naturally there will not a side of the cylinder, phi will be 0. Correct. What is the net outward flux through the cylinder? So from this side, it is this thing from this side is so that outward will be what? You just sum up these two left and right. This will become the net outward flux. FL and FL, this thing, they will be both simply add up. Correct. What is the net charge inside? If you add up, then this comes as 3.14 Newton meter square upon Coulomb. So net charge is nothing but Q is nothing but epsilon 0 to 5 or 3.14 into 8.854 into 10 raised to. So this is the basically charge inside the cylinder. Correct? So this solves your example. Now, in this chapter, only few things are remaining. Let us cover those also, and then we will wind up. Correct? What are the applications of the basically Gauss law? So one application is suppose you have a charged wire infinitely long. Due to this, suppose you want to find out the P at P, electric field at P, then what we will do? We will make a Gaussian surface through this. And since it is wire, so it is better to make the Gaussian surface as cylinder. This is cylindrical Gaussian surface. Now, suppose if you have a charge density of lambda, means charge per unit length or is lambda, charge density is on this wire is lambda. So this is a plus. Then in this enclosed, suppose this is your L and radius is R of your Gaussian surface. Naturally, this point is at R, we have to find out the, we can take this as a small, it will be since we have to find out the electric field at a distance r from the infinitely long wire. Correct? So, as you see, since here, due to this wire, what will be the electric field? This electric field will be in this direction, or if you can take this segment or this segment, then here electric field will be like this, electric field will be like this, but its vertical component, they will cancel out, and ultimately electric field at P will be perpendicular to the wire. This is what is going to happen. But direction is okay, but what about the magnitude? So we know by Gaussian formula E to A is nothing but Q upon epsilon 0. So E we have to find out. Q, what is Q? So lambda into L will be the charge enclosed by this Gaussian surface, because L length of wire is only inside the Gaussian surface, divided by epsilon 0. Now A is what? A is your this thing, 2 pi r L. A is the surface area of the Gaussian surface. Correct? Through this flat, through these surfaces, there won't be any electric field, because area vector will be normal to electric field. There won't be any electric field. So just forget about this. We, the circular area, lateral area is the only effective this thing. So here, basically, if you see, so this is the electric field at point R. If you are given lambda, you can always find out the electric field, and direction we have already seen away from the, suppose negative charge is there, then it will be towards the wire. Correct? Now, this is long wire. Correct? Same formula is there. And direction is radially outward, radially inward, negative charge. Correct? Then infinite plane sheet is there. Suppose now, just see. Suppose infinite plane sheet is there. Your charge density is there. Correct? Suppose this charge density is sigma. Now, for finding out the, suppose our idea is before this sheet, perpendicular distance, our idea is to find out, suppose this is the distance, if this is the point P, our idea is to find out the electric field due to this plane charge sheet. Correct? So here also you can see, you can make the Gaussian surface just see here electric field is, and this is your, here also delta S is there, and this is your, correct? So E into delta S is equal to Q upon epsilon 0, or E is nothing but Q upon delta S into epsilon 0. But here you see, since there are two surfaces, one is in this direction, another is in this direction, so you have to multiply by 2. So you have to multiply by, sorry, with the denominator. What is this? It is nothing but charge density, correct? Sigma upon 2 epsilon. This is the electric field at a perpendicular distance at any point. It is not dependent on the r distance. So due to the plane sheet infinitely long aerially plane sheet, the electric field is uniform and the value is basically sigma upon 2 epsilon 0. Correct? So this is due to the plane sheet. So here again positive sheet is there, then field will be away from the sheet, both sides. Negative sheet is there, negative charge is there, then electric field direction will be reversed. It is independent of the distance. Field is uniform. Field is perpendicular to the surface. Correct? So this is how we can. Next we can see a uniformly charged spherical cell. Correct? So you have a spherical shell. You have a, suppose this is your shell. Correct? This is the R, and you have sigma charge density on this thing. So naturally, what is the total charge? Sigma into 4 pi r square. Now, suppose I want to find out at a point P which is outside the cell, correct? So what will we will do? Draw the Gaussian surface, and this distance is basically r, correct? So at P, we have to find out the electric field. What is the area of the Gaussian surface area, this thing, and what is the charge enclosed? Charge enclosed is nothing but total charge upon epsilon 0, correct? And EP, we can write it as Q upon 4 pi epsilon 0 r square. It is the same as what we have calculated for the point charge. That means even shell, if the surface is having the charge, then the charge it is considering as a on the center, and the same as we used to calculate with the point charge, correct? So when r is greater than r, if any point is outside the spherical shell, then you have at any point this will be the electric field, and direction of the electric field is nothing but here your field lines. Suppose field lines will be like this. So direction of the electric field will be nothing but, suppose it's a positive charge. If it is a positive charge, correct. Now when R is R, then EP is nothing but you can substitute as 4 pi epsilon 0 R square. But suppose when R is less than R, then what will happen? Suppose let us see, this is the Gaussian surface we have made. Suppose we want to, suppose this Q point is there and it is R and R is less than R. Then what is the electric field? EQ into 4 pi R square is nothing but Q enclosed upon epsilon 0. But this quantity is 0 because there is no charge inside this Gaussian surface. All the charges, they are at the surface of the shell, not inside the cell. Then what will happen? That means inside the cell, your electric field is 0. The field inside the cell is 0. Outside behaves like a point charge. Field is discontinuous at surface, of course, because up to the surface it is there electric field. Immediately it becomes 0 inside it. Correct? So this is this thing. Now let us do this question. It is related to your Gauss, this thing. An early model of atom considered to have a purely positive or nucleus of charge JE. Correct? Nucleus of the nucleus is basically your JE, surrounded by uniform density of negative charge up to the radius R. The atom as a whole is neutral. For this model, what is the electric field at a distance R from the nucleus? R from the nucleus. Correct? So let us solve this problem. First of all, suppose we take this point. Here it is R distance, this point is there, or we have to find out the electric field here. So let us draw a Gaussian surface. Correct. Now we have to find out the total charge inside this Q enclosed. That is the most important thing. Correct. In this case, here basically atom is electrically neutral. That means ZE is the positive charge inside the nucleus. So naturally, minus ZE will be the negative charge outside the nucleus. So let us see what is the density of negative charge. Suppose rho is the density of negative charge, then 4 by 3 pi r cube is nothing but minus ZE. Correct? So here our this thing is ZE upon 4 pi r cube. Correct? Now R is basically less than R. So phi is what? Phi is basically E, electric field at R distance, into 4 pi R square. That is the surface area of a Gaussian surface. Correct? What is the Q enclosed? Q basically is enclosed is nothing but the nucleus is enclosed entirely. So ZE charge is there, plus your negative charge, that is 4 pi R cube upon 3 into rho, that is the charge density. Correct? If you put the value of rho, this will come as ZE minus ZE R cube upon R. This is the charge enclosed. That means ER at resistance R, it is nothing but ZE upon 4 pi epsilon naught 1 by R square minus R upon R. When R is, this will be the electric field when you want to find out the electric field inside the atom. Correct? This electric field will be directed radially outward, because if you make the electric field lines, they will be radially outward. In case if R is greater than R, then whatever atom is there, nucleus is there, both positive and negative charge, they are equal and opposite. That means Q enclosed will be 0. Suppose if we make a Gaussian surface, that means if R is greater than R, then E will be 0. Correct? Even R is R also correct, then E will be 0, because if we make the Gaussian surface just enclosing this atom, then positive charge and negative charge both are same. So in fact, the net charge will be 0. So at this also it will be 0. So this is how this question you can solve. So you have seen from this thing, you have seen in this chapter all the things of NCERT has been covered. I have explained each and every derivation and this thing. Now, this chapter, what remains is the exercises. So, our next video will be to do the NCERT, all the exercises. Then it will complete your first chapter of the class 12th, that is charge and electric field, complete in all the sense. Correct? So, just share your opinions, your thoughts, that how was this video. Please subscribe my channel, and soon I am going to upload that video also, doing all the 25 exercises of this NCERT chapter. Thank you very much.